Using the thermodynamic and the phase field modeling approach, we can build a theoretical framework to predict the phase stability and the microstructures and how they are related to macroscopic functional properties.
Hi, my name is Quanxi, a professor at the University at Buffalo. I'm the editor-in-chief of Journal Material Research. I would also like to introduce over here Professor Long-Qing Chen and also Professor Bo Wang from Pennsylvania State University. So you guys have recently published a very significant review article in Journal Material Research, which is related to the strain engineering of ferroelectric thin films from really phase field simulation, that kind of perspective. So in your article, you highlight the importance of close interaction between theoretical modeling and also experimental work in discovering new physics and also enabling new functionalities in ferroelectric material, right? Both in bulk crystals and also thin films. So from your perspective, how can experimentalists better take the advantages of simulations and also calculations to guide their design and also exploration of new directions in ferroelectric research?
Yes, I think that's a great question, and that's also what we want to achieve in this review article. So in this article, we did a survey of the recent progress in both experimental side and theoretical modeling side on this KNN thin film epitaxial ferroelectrics. And one key aspect we stress is that using the thermodynamic and the phase field modeling approach, we can build a theoretical framework to predict the phase stability and the microstructures and how they are related to macroscopic functional properties. We present these concepts into what we call strain phase diagram. Basically, it describes the phase stability as a function of temperature and its strains from the substrate. And this type of strain phase diagram could be useful guidance for experimentalists to determine the growth conditions, the substrate to choose that can help stabilize specific phases and specific domain structures, which will help enhance the functional properties such as the dielectric permittivity and piezoelectric constants.
What are the biggest opportunities for ferroelectric thin films?
Okay, yeah. From my perspective, especially for this paper, we're focusing on this potassium sodium niobate oxide, which is so-called lead-free ferroelectrics. There's a growing interest and a push forward to this lead-free system because of the environmental and the sustainability concerns. And with the goal for developing this KNN thin film is to explore its potential to serve as a substitute material for the lead-based system like PZT ferroelectrics. And for application-wise, I think the epitaxial ferroelectric thin film is promising for high density information storage used in non-volatile memory devices. And actually, there's another growing interest which we are exploring recently is to use the ferroelectric thin film for electro-optical modulation devices, which turns out to be critical to transform the optical signal to electric signal and this it turns out to be important for the data centers for AI and quantum computing applications.
So some of the new really hot directions, including like Bo mentioned, memory applications, which are integratable with silicon, such as hafnium oxide ferroelectrics or hafnium oxide based ferroelectrics or woodside based ferroelectrics, and also the electro-optical applications for quantum computing. I think these are the really emerging, at least right now, areas for ferroelectric applications.
So what advice would you offer to early career researchers who are interested in entering this field?
Well, certainly phase field method is still based on the fundamental thermodynamics, but for inhomogeneous systems. So to get into phase field is not that different also from doing density functional theories or doing molecular dynamics simulations, or in a sense actually doing experiment. To me, one is really you want to build a solid thermodynamics background, but also build really thinking skills. And that's no different from doing other things. Really, when you want to do phase field simulations, what problems you want to solve or what questions you want to answer. So, but then you use the phase field method as a tool to whether it's test your hypothesis or actually try to explain an experiment. So to do those also, you want to understand actually experiment. Even doing a simulation, you always keep like experiment in mind. You're going through the process, whether you are talking about thin film on a substrate, you imagining the real, rather than really just have, I change some parameters and just see what happens. So, but for somebody has no experience, certainly now there are codes available, whether they are open source codes or whether they are commercially available codes. I think they can actually start from there in terms of getting the codes to start with. I have a former postdoc who came as experimentalist, but within 1 or 2 months, actually, he was able to do simulations, and actually that's led to a number of high impact publications.